Hello guys, welcome to the solutions video of Google Codejam Qualification Round 2022. So as you can see, I was able to solve these 4 problems during the contest, and I'll be sharing my solutions for these very 4 problems. So let's move on to the first problem. Right. In this problem, we basically have to print this pattern. We'll be given a period or a dot which will be surrounded by dashes to above and below, and pipes to the left and the right, and then we'll be having plus signs in each corner. Right. So this is what the question is asking for. So for each dot we'll be having these pipes to the left of it, and plus signs to the corners, and dash signs or the dashed signs to above and below of each dot. So for each row which contains a period, we'll be having a row to above and another row to in the below of it. Similarly, for each column which contains the dot, we'll be having another column to the left of it and another column to the right of it. So for each row R, we'll be having 2R plus 1 rows in total, and for each C given, we'll be having 2C plus 1 columns in total. So our resultant grid will have 2R plus 1 rows and 2C plus 1 columns. So we'll be placing the dots at positions here. Considering zero based indexing, we'll be placing the dots at 1, 1, 1, 3, 1, 5, and so on. And then again for the next column or for the next row, this will be for this we will be having a dash here, and now this is 0, 1, 2, 3. So we can again put our dots at the third row. So again we will apply the same logic, like 3, 1, 3, 3, 3, 5, and so on. So so that was the first problem, and now for each dot we can iterate for each dot and then put a dash sign above it and one below it, one pipe to the left of it, one pipe to the right of it, in this way. And then we can fill the remaining places using a plus sign, and then we have to make sure that we change these ones, that is 0, 1 and 1, 0, 2 dots, right? So that's it, and so let's jump to the code directly. So here I am defining my grid, which consists of 2R plus 1 rows and 2C plus 1 columns. And now I am iterating from all the rows starting from 1 with a gap of 2, that is from 1, 3, 5, and so on, and doing the same for the number of columns starting from 1, 3, 5, and so on. And then I am filling the grid, and finally I am changing the grid positions at 0, 0, 1, 0, and 0, 1, 2 dots. And this is my code, right? So now let's move to the second problem, which is 3D printing. In this problem we have 3 printers and 4 cartridges. So we have 3 printers like this and 4 cartridges of having the colors cyan, which I am denoting by C, magenta by M, yellow and black. So printer 1 has C1 colors of cyan, printer 2 has C2 colors of cyan, printer 3 has C3 colors of cyan. Printer P1 has M1 colors of magenta, P2 has M2 colors of magenta, and P3 has M3 colors of magenta. Similarly, this will be Y1, B1, Y2, B2, Y3 and B3. Right. Now we have now the total amount of ink that we need to print a single D is exactly 10 to the power 6 units. So basically using these 3 printers and colors, we have to print 3 Ds required for the logo of the contest, and each D has to be printed with colors adding up to exactly 10 to the power 6 units. And also we have to fulfill the criteria that the printer must have at least the required amount of ink so for each of its 4 color cartridges. So right, so basically from among these colors we have to choose any color. It can be either simply cyan or magenta or yellow, or we can use a combinations of colors like cyan plus magenta plus yellow and so on. Now now we have to choose this color in such a way so that the color of colors chosen, their values, the number of colors chosen for cyan plus the number of colors chosen for magenta plus number of yellow colors will sum up to exactly 10 to the power 6. So we can approach this problem by choosing the minimum values for each such colors. So it is obvious, it will be obvious, say if we choose C1 as the minimum color of cyan among all such printers, it will be the limiting value. For example, if cyan has the colors 5, 4, 3 for P2, printer P2 and P3, so we can choose these 3. As it is evident, printers P1 and P2 can always produce these 3 colors of cyan, but it's not the true otherwise. If we choose 4, this P3 will not be able to produce 4 colors. So for each such colors we will be choosing the minimum from each such rows. So we'll be choosing the minimum number of colors for cyan available among all the 3 printers. Same for yellow and same for blue. Now let's denote, say the minimum value for cyan is plus small c, for magenta it's plus small m, for yellow it's small y, and for black it's b. So this is my required sum. So now this fulfills the criteria that all 3 printers will be able to produce these colors, right, or the color required to print these Ds. All 3 printers will be able to produce this since these are the minimum colors. Now if sum is less than 10 to the power 6, then it will always be impossible to print any colors. But say sum is greater than equals to 10 to the power 6, we will always be able to get one answer. Now after choosing this after choosing these minimum values and getting a sum which is greater than 10 to the power 6, we will simply take the difference s minus 10 to the power 6 and then keep subtracting the excess from each of the colors chosen. For cyan, we suppose subtract D such that cyan becomes 0. From magenta, we subtract E amount of colors, it becomes 0. And then from yellow, we subtract F amount of colors, so it becomes Y. And black remains as it is. Now Y plus B will be 10 to the power 6, and these will be our required colors chosen. So these will be our required colors chosen. Right? So that was the problem. Let's jump to the code. So vector C will store the colors cyan, M stores magenta, Y stores yellow, and K stores black. Now from each vectors I choose the minimum elements, and then I check their sum. If it's less than 10 to the power 6, it will be impossible. If it's exactly equals to 10 to the power 6, then I don't have to subtract any value. I can simply output these numbers, or else I will take the difference and keep subtracting the required numbers from each of them. So I subtract difference from C0 if C0 is greater than difference, or else I change to C0 to 0, and then I also decrease the difference, and I will keep doing for all these numbers until my sum becomes 10 to the power 6. So that's it. I do it for all such colors, and then I finally return my answer. For whichever color it will be last satisfied. Right. So that's it. Now let's move to the third problem. In the third problem, we'll be given a collection of n die. The ith die will consist DSI, which consists of SI sides showing integers 1 through SI. So it's a simple problem as well. We are given dices of various sizes starting from 4 to 20 inclusive. We have to put the dices in a straight. That is, we have to check whether the dices can be put in a straight line to form a sequence like this: 1, 2, 3, 4 up till n. Right. So what we are gonna do is that we have to output the maximum number of dices which can be put in a straight. So 1, 2, 3, 4 up to m. Let's say we can put up to m dices in a straight. So we will output the value m. Another thing is that if we have a size I, dice of size Si, then it can be used to generate dices of sizes 1, 2 up to Si minus 1. So let's take an example. So let's say we have 4, 4, 5, 5 and 6. These are the die we have. So let's check how we can put them in a straight. So 4 can generate 1, this 4 can generate 2, this 4 can generate 3, and this 5 can generate 4, 5 and 6. So from our given die collection, that is something like this. So from our given die collection, we'll simply sort it. So if our array would have been 5, so it's most optimal to generate the smallest number from the smallest die one from the smallest numbers present and continue it further. So we'll sort this array and check how many die we can put in a street. So 4 will give 1, 4 will give 2, 4 will give 3. Since it can generate a die of size smaller than it, 4 will give this 4 will be 4 itself. This 5 will give 5, but now this 5 cannot generate 6, so I will keep it as 5 only. But this 6 can generate the greater number, the number just greater than 6 and then 7. So I'll build my possible array like this, and then I will store them in a set to remove all such duplicates which may arise in this array. So my set will consist of 1, 2, 3, 4, 5, 6 and 7, and I'm going to simply output the size of this set. I'm simply going to output the size of this set, and this will be the number of die, or m, maximum number of die which can be put in a street. So right, let's see the code now. So this is my input array, this is my sides array, or the array which will be building from this A, and this is my set possible, where I'll be storing the final array elements into my into this set. I'll be sorting the given array, and then I'm going to build the sides, or the sides which will be which we will be able to generate from each of the previous side, from each of the previous die, right, just like this. So our sides array will be storing 1 here, 2 here, 3, 4, 4, 5, and whenever we'll be missing a greater element, or will be unable to generate the next higher element, that is 6, we'll be continuing the number 5 here, and we will continue this until the end of the array. And then I'll be inserting all these elements into my set, and then simply output the size of this set. So this was the code, right? So let's move on to the fourth problem and the last problem, to which I'll be sharing the solutions. Now the fourth problem is a very interesting problem. Here each of these n modules have a fun factor I. The fun wheel gets from a chain reaction is the largest fun factor of all modules that are triggered in the chain reaction. So this is the animation. So wheel is going to trigger one of these initiators. Initiators are those modules which do not have another module pointing to it, right? And so what we have to do, we have to choose some order of choosing these initiators. Say here our initiators are 50 or 40, so we will choose a particular order, either 40 before 50 or 50 after before 40, so that our fun factor will be maximum. So in a chain reaction, for a particular chain reaction, the fun factor for that chain reaction will be the maximum value we encounter during that process. So if we start from 50, we'll go to 20, we'll go to 60. That will be our first chain reaction, and the maximum value which we'll find is 60. That will be the fun factor for my first chain reaction. Now once a module has been initiated or has been triggered, it cannot be triggered further during another chain reaction. So again, when we activate this module 40, it cannot activate 60, and so during this process our maximum fun value is 40 itself. So our total fun value is the sum of the fun values obtained during each chain reaction. So in this case it will be 50, 60 plus 40, 100. Now if we choose the module for initiator for starting the chain reaction, in this case our 40 will go to 60 and our fun value for this chain reaction will be 60, and then again for we'll start 50 chain reaction from 50, which is an initiator. It will go up to 20, but and then 60 is already triggered, so it cannot trigger 60 again. So our maximum fun value for this process will be 50. So but the fun value this time will be 60 plus 50, 110. In the second case we are getting a greater fun value than in the previous case. So that is what the problem is saying, that we have to choose a particular ordering or order of selecting these initiators such that the fun value obtained will be maximum. That is, he triggers the initiators in the best possible order. Right? That is what the question demands of us. So let's make some observations before jumping to the solution. So we are given n modules, and each n and the ith module will be pointing to exactly one other module. So if it's 2, it will be pointing to 1. So if it's 3, it will be pointing to 2, or let's say 1. Another criteria is that a module I can only point to modules having index number less than I, that is from 1 to I minus 1. So our first observation is that these modules will form a directed tree or directed trees. These n modules form directed trees. Reason, since as I told just before, since each module can call a single other module, and there will be no, and another important thing is that there can be no cycles, since each module will be calling another module having index number lower than it. For example, 5 will call a module 4, 4 will call a module 3, 3 will call a module 2, 2 will call a module 1, but 1 cannot call 5 since 5 has a higher index number than 1. So cycles are not possible, and so we are so our assumption or our observation is correct that these n modules will be forming directed trees. So our trees will be of will be something like this. So in these trees, these leaf nodes will be our initiators, since they do not have any module pointing to it. So each initiator will point to some module like this, which will be further pointing to another module like this. So now if we have an array where there may be two such nodes which point to abyss, right? Point to abyss, so a module points to abyss if if it contains the value 0. What I meant to say is that so the first module points to 0, which means it's an abyss. So there can be multiple such elements in this array which can point to abyss, that is 0. So it's evident from this diagram that the modules which point to abyss are nothing but the root of this tree. Are nothing but the root of this tree. So from whichever module we start, we will always end up at this module, the module which will be pointing at the abyss, or the root module, right? So there can be multiple such directed trees forming due to multiple such modules pointing to the abyss. So we can have another such tree. This will be another. And this can be another such tree. So these will be such our modules can be in this form of such disconnected components as well. So this will be our modules form a collection of directed trees, or you can call them a forest. So let's try to build our solution. If we build the tree structure for the third example, we will get something like this. This will be our root node. This will be 1, 2, 3, 6, 8, 5, 4 and 7. Their corresponding values will be 100, 90, 90, 80, 100, 100 for this one, 100 for module 3, 100 for module 2, and that's it. So we can see here, to initiate node 3, we can either choose node 6 or we can choose node 8. If we choose node 6, our value for triggering node 3 will be maximum of 100, 100 plus 100, or so this is the value for node 6. We are consuming this branch first. So maximum of 100, 100. This is my chain reaction. So whichever will be the maximum value, we will choose that, plus 100, which will be for separately triggering initiator 8, which we will get 100 for this one as well. Or if we choose the initiator 8, so it will be maximum of 100, 100 plus 100. So in this case, it makes no difference, and we will get the maximum value for triggering node 3 as 200. Similarly, for node 2, we can either choose the path originating from node 3 or the path originating from node 5. So let us define a DP array. Where a DP of node I stores the maximum fun factor that can be obtained to trigger this node I. So let's say for this example only, so for triggering node 2, we can either consume this branch or consume this branch, right? So our DP value or the value for the DP of node 2, let's define that as current node per node, we will get dp of current node as the maximum value among all its children, and for maximum of a of current node, comma, the mean value of the node we are choosing. Plus the sum of the values of all its children, that is sum of dp node child, sum of the dp of all its children, this is a particular child, minus mean value of the child we are choosing. So this will be our entire dp state. So let's try out a dry run on our previous example. So here is our example test case, and let's perform a dry run on it. So let's say for we are at node 3. So we can either consume this branch, or that is we are choosing this initiator first, or this branch. So for dp of node 3, for building node 3, we will first need the sum of all the subsequent nodes, sum of the dp of all the subsequent nodes. So for leaf nodes, which are the initiators actually, so the dp for the leaf nodes will actually store the value of its, will store its actual value of fun factor. Sum of the dp of the children of node 3 will be actually 100 plus 100, 200. And so we can build dp of node 3 using the state we have defined. So dp of node 3 will be maximum of current value of node 3, that is 100, comma 100, plus the sum of all its children minus the mean value of the node we are choosing, 100. In this case, we will get 200. Now, if we choose this branch using node 8, in this case it will be similar, which will be maximum of 100, 100 plus 200 minus 100, which will be 200 as well. So after performing a dry run on the node 3, we get activating 3, or for triggering 3, our values will be 200, comma the minimum value of 3, which will be 100. Since this is 100 and the minimum value we have encountered up till 3 is 100, and we have also updated it to our new value, which is 100. Now let's check for 2. Now for 2, similarly, we can choose this branch. If we choose this branch, then our dp for node 2 will be the maximum of the current value of node 2, which is 100, comma the minimum value of the node we are choosing. In this case, first it's 100, plus the sum of the values of the nodes, which is 200 plus 80, which is 280, minus the minimum value of the node we are choosing, which is 100. So 100 plus 280 minus 100, that will give me 280. Now let's choose the other branch. This branch. Then our new value for dp2 will be dp of node 2 will be the maximum of its current value, which is 100, 80, plus the sum of the values, which is nothing but 280, minus the minimum value we are choosing, which is 80. So this will be, in this case, 100 plus 200, and we'll get it as 300. So since 300 is greater than 80, so the maximum fun factor we can achieve for activating or triggering 2 will be 300. Right? So 300, comma, but in this case we are updating the minimum value we are obtaining here, which is 80 to 100. That means if we have started the chain reaction, since the maximum value is 300, which means we have started the chain reaction from this node first before we can activate 2. And while doing so, we have updated the minimum value 80 to 100. So the minimum value of this node will again be 100. Right? So let's go to our final node, which is node 1. So in node 1, we can choose this node, or this branch, or this branch, or this branch. So let's first choose this branch. Then our dp of node 1 will be maximum of its current value, which is 100, 100, plus the sum of its nodes, the sum of the values of its nodes, which are its children, that is 300 plus 90 plus 90, which will give me 480, minus the node we are choosing, that will be 100. So we will get it as nothing but 480. Right? So when we are choosing the branch originating from node 2, we are ending up with a value of 480. Now let's choose this branch. In this case, node 1 will store maximum of 100, 90, plus 480, which is the sum of nodes, and the minimum value of the node we are choosing, which will be 90. And we will be getting it as 100 plus 390, which is 490. So since 490 is greater than 480, we will be updating 480 to 490. And it will be the same as in the case of triggering node 7. So we can choose either node 4 or node 7 first for triggering node 1, and then the branch originating from node 2. So in this way we can build our answer. And we can check our answer will always lie in our root node. That is the node which will be pointing to the abyss. That is our node, that is always our root node will store our final answer. So if we have trees like this, directed trees like this, this is 1, this root node will be 2, this root node say it's 3, then our total answer will be the sum of the DPs of each of these root nodes, right? So the sum of each of these root nodes, that is DP of node I and node 1 plus node 2 plus node 3 and so on. Since these are disconnected, and the answer will be separately calculated for each such nodes. DP of this node will calculate the maximum fun factor for triggering all the nodes in the right order to get the maximum fun factor for this connected component, right? So after we take out the sum, we will simply output it, and that will be our final answer. So let's quickly jump to the code. So here is our code. So here we are receiving the input like this, where receive will store nothing but the root nodes over all such directed trees, right? So that we can run a DFS from each of such root nodes and output the sum of the fun factors we will obtain for each such root nodes. So here we'll be running the DFS from here, from each of these root nodes, and then we will be adding the maximum fun factor for this. So as we see during the dry run, that each node will be returning two values: the fun factor, the maximum fun factor that is required for triggering itself, and also the minimum value up to that node. So this is our DFS function. We are visiting whichever node we are we mark it as true, and if the node is a leaf node, that is one of our initiators, that means our minimum value will be its actual value itself, and our DP current will also be its normal value, right? So if the node is not visited, we continue, or we start a DFS from its child node, and then keep adding. This sum will store all the DP values of its nodes, which will store their corresponding maximum fun factors. Now this is my minimum value array, which stores the minimum value which will be updated for each such current node we visit. So if we are at the node 2 and our minimum value has been updated to 100, so it will be storing 100. Or if it has not been updated, it will store the minimum value among all its children nodes, right? So here is my state, which will be storing the maximum value among all the children nodes, where I first find the maximum of A of current node, it is its actual value, then the minimum value of the node, plus sum of all its children node minus the sum of the minimum value of the node we are choosing. So it has to be subtracted from sum, otherwise we will be double counting it. And finally I return for each such node my maximum fun factor for triggering that node and the minimum value up to that node, right? And simply after finding the sum for all such disconnected components or the root nodes, I will output this total, and that is our answer. So these were the solutions of the 4 problems of Google Codejam Qualification Round 2022. So these were the solutions of Google Codejam Qualification Round 2022. So if you have liked the video, do share, like and subscribe, and thanks for watching.